Yeah, in our previous lecture, we have covered spark gaps, including sphere gaps, uniform field gaps, rod gaps, and electrostatic voltmeter, etc. We have noted that resistive dividers compete with electrostatic voltmeters and are cost effective. So, in this lecture, we will study resistive dividers and other resistance based measuring systems. The first in this series is ammeter in series with high impedance or high resistance. Now this resistor is the high value resistor. This is to keep the loading on the source very small. Now there is an ammeter connected here which is in series with this resistor and grounded here. So as you know, the internal resistance of ammeter is very small, so ammeter drop is neglected. So simply the relationship, the voltage, terminal voltage V of t is R into I of t. I of t passing through this. This is also same and this is also same. So current in this branch is neglected. I equal to 0. Now, average current indicating instruments such as moving coil meters are used for this purpose. The instrument is to be protected. This is the protective device. It may be a paper gap, a glow tube, or a Zener diode, which have voltage limiting characteristics. Now, fundamentally, the time dependency V of t could be measured by an oscilloscope, provided if R is a pure resistance. Let us see what is the effect of R and R in next few slides. So this is the basic principle: high voltage or low voltage for all voltage measurements. This is the principle, basic principle. And if R is pure or doesn't change with anything, then this relationship will hold. And if R is a constant, the measurements will be accurate. But that is not so in general. Now the stability of resistors, voltage and temperature dependence. So these are the complications. All types of resistors, irrespective of type of resistor, are temperature dependent. Their resistance is temperature dependent. The value of temperature coefficient alpha for different resistors is given below. That is, carbon composition, it is 1200 ppm, wire wound 0.00017 per degree centigrade. Carbon film, this is the value in the range, and this is the range for metal film and metal oxide and thin film and thick film. These are the resistance values of resistivity values, alpha values for various resistors. These resistors we will study in detail in next few presentations. Voltage and temperature dependence of R. So apart from temperature dependence, voltage also, often resistors may also show some voltage dependency. See, this is the resistance value approximately with temperature and voltage dependence included in this. So here you can see for small deviations means delta t and delta v. If the values are small, then linear approximation can be done like this: 1 plus alpha t and 1 minus beta v. With voltage, a little bit decrement in the resistance is observed with temperature, little bit increment in the temperature, resistance is observed. So these variations are unfortunately directly proportional to the voltage to be measured and then impede the accuracy, resulting in distorted waveform apart from erratic magnitude of magnitude under DC. Distorted waveform, here distorted waveform is written. The reason is with voltage the resistance value decreases. So the measured voltage, and then for example if you are measuring sinusoidal voltage like this, you may be estimating a wave like this. The reason is the decrease in the resistance value. So this is the estimated, this is the actual. So there is an error with voltage also, right? So the distortion is observed. Now the second thing is limitation of series resistance on voltage measurements. What are the limitations? One is power dissipation and temperature rise. Of course, for high voltages, if voltage is increased, V square by R losses will increase, and then power dissipation will be there inside the resistive element, and then that will cause temperature rise, which is not good. Why it is not good? We will see. Temperature effects on long-term stability. The third point, if you see, temperature effect will also change the internal structure of the resistor, and then ultimately it will change the value of the resistance over a long period of time. And the second point is source loading. This is discussed later. Source loading means that resistive element will also take some current, unlike electrostatic voltmeter we have studied. So here the current values are significantly high compared to electrostatic voltmeter. So source loading is another problem. And voltage dependence of resistive elements and their long-term stability. Here also internal sintering may happen inside the resistances, and then it may affect their long-term stability. So think a moment, one more thing, here, can we eliminate or minimize this temperature and voltage dependence for accuracy? Somehow can we manage without actually changing the material? Because as you have seen, all the materials exhibit some temperature dependence. Of course, you also go back and then see, I have given you the coefficients alpha, compare them and try to observe whichever is having lowest temperature dependence. So this gives you some understanding, so which material to be used and all. So in order that it the temperature sensitivity is less. So other than that, without changing the material, can we use some method to eliminate or minimize temperature and voltage dependence? So this is the next generation of resistive measurements. This is resistor divider. So here, instead of one single resistor, we have two resistors, and the voltage you can simply show, the current is same, right? V by R1 plus R2 is equal to V2 by R2. If you apply that, you will get this equation or this equation. This is with the time. This is for DC, it can be applied. Now you see here the ratio R1 by R2 can be written like this: R10 into 1 plus alpha delta T into 1 plus beta delta V divided by R20 1 plus alpha delta T 1 plus beta delta V. You can see this term and this term gets cancelled, this term and this term gets cancelled. Now it is simply R10 by R20. So irrespective of temperature variation and voltage variation, of course within certain limits. R1 by R2 is equal to R10 by R20. But this happens provided the materials of resistors and electric stress is same. Electric stress, stress across the resistors, this delta V corresponds to in fact that only. Voltage in the above corresponds to field stress only actually. So if voltage stress and if voltage stress and material means same delta T should be there, no? So material of both resistors R1 and R2, both resistors have same material and same electric stress, then these coefficients gets cancelled. The influence of temperature and voltage can be neglected on the dividers. So then voltage measured here. This is a voltmeter actually. Construction I have to tell you. So R1 and R2 are in series, and here since this is a voltmeter, I10 through this channel, through this path is 0. So entire current flows through R2 only. Whatever comes from R1 flows through R2 only. So there is no current through the voltmeter. Approximately 0. That's what it is. So with this we can have this kind of ratio, and then we can measure the voltage, terminal voltage using this method. But in olden days the accurate measurement of V2 was difficult in earlier times, for low voltages, as only electrostatic voltmeter of limited accuracy at low voltages had been available at that time. So for low voltages, unfortunately, electrostatic voltmeters have the force of attraction is very small, and then there are certain limitations on accuracy and all. So, but modern electronic voltmeters have with high internal impedance and high enough internal impedance, and are very accurate, high accurate for DC voltage measurements, and are easy to use also. So this way the voltage divider mentioned here can be used, and the principle, as I pointed out earlier, the principle is same for high voltages as well as low voltages. But whether there are any differences or not, if principle is same, everything is same. So resistive dividers for high and low voltages, what are the differences? So think a moment, what could be the differences? Differences should be related to higher and higher voltages, right? So what are the effects at high voltages, and how to address them, and what changes that will cause in the either construction or anything else and the performance or design of the resistive dividers for higher voltages. Now the first thing is upper and lower limits on resistive measuring systems for high voltages. So what are the upper limits? The upper limit is set by the heat dissipation, and heat transfer by natural convection only would restrict the upper current limits to 1 to 2 milliamperes. So as I have pointed out in previous slides, so if the heat generated within the resistance causes the temperature to be very high, the internal structure itself gets modified, and the resistor may lose its performance, and its stability is also in question. Therefore, in order to protect the resistance itself, our currents, maximum currents that can be allowed, upper limits on currents is 1 or 2 milliamperes. This not only sets on maximum current, but also sets upper limit on voltage also, because voltage, as we increase the voltage, current is expected to increase for a given resistance value. Therefore, this sets the upper limit on voltage and upper limit on current. So, and lower limit on the resistance value. That's what it is. Now then, one more problem is, which sets the lower limit is, even with the best insulating materials, the leakage along the resistor column or the supporting structure would be around 100 microamperes. So the minimum current that the source has to supply is 100 microamperes. So this is the minimum limits, but this sets the lower limit of current. How? Just think about it, how it sets the lower limit of the current. I want to use a resistance, very high, so that only 100 microamperes, roughly around 100 microamperes the source will supply. Do I need to make my resistive system having resistance lesser than the surface leakage and all? So let us see, think about it. So let us design limitations due to leakage along the resistor column or structure. So first let us see what are all the leakage components. Say due to corona, maybe from here, charges may go, and even from everywhere charges may go, little bit leakage may be there. This is one sort of leakage. Another is surface leakage, like this leakage current, and then even along the resistors, and then even along the resistors, like this leakage surface, along the surface, and the currents will leak from high voltage to ground, right? Now, what is the effect of these currents and how this will affect the design? Let us understand the system when the leakage is there. So if only resistances are considered, assume that DC conditions and all. So you can approximate this structure using resistors, and then this is resistors of resistive column, actual divider, and this is due to surface leakage or leakage along the structures. Let us say this as RS or RL. So like this, and then ground. Okay, this is R, this is R, this is RS, this is RS. RS will be having different values. R may be uniform. RS, let us say RS1, RS2, RS3, etc. Because along the column also the resistances will be different. Now consider a case if RS is smaller than R. RS is smaller than R, which will dominate. R, current through leakage, is higher than the current through this. That's what it means, right? Because this voltage across these resistors is same V, some V. If RS is small, heavy current will flow through this and small current will flow through this, right? So if our divider resistors are of higher value than the surface leakage resistances in terms of leakage, or in other words, if the current through the surface leakage is more than the current through the divider, then what will happen? Which will dominate? What will happen? The surface leakage current is high, so, and resistance is small. In parallel, always smaller resistance will dominate. This will dominate. This has no effect. Then the fundamental principle itself will fail. That is why always the current through the divider must be more than the current surface leakage current. So in fact, in all practical cases, it should be around 10 times the leakage current. Otherwise, basic function of the divider itself will be in question. So if the leakage, surface leakage current is around 100 microamperes, then the divider current should be 100 into 10, 1000 microamperes. Means what? 1 milliampere. Roughly around 1 milliampere. This sets the lower limit on the insulation. This sets the lower limit of the current on the insulation. It cannot be smaller than 1 milliampere. The divider current cannot be smaller than 1 milliampere. So this is the design limitation due to leakage current along the resistive column or structure. I hope you understood. And then problems under sudden voltage drop or breakdown. Now for DC alright, we have given the resistive circuit like this, but under sudden conditions like the sudden voltage drop. How sudden voltage drop will occur? When breakdown occurs, usually sudden voltage drop will occur. Then under this condition, under sudden conditions, the stray capacitances, stray inductances will come into picture. So in this case, stray capacitances will come into picture unless the resistors are wire bound resistors. That is a different story. Now we'll come back to that again. So the stray capacitances are 3-4 types. That here the stray capacitance of each element to ground like this, like this, like this. These are stray capacitances. And then to high voltage also there may be stray capacitances like this. I'm trying at some points, but entire surroundings you have to imagine. And apart from these, between these two rows are what we say, helical structures. These parallel capacitances may also exist. So this stray capacitance system, under sudden voltage drop, actually the voltage drop, voltage distribution does not follow resistances, but it follows capacitances. Sudden means high frequency. High frequency means capacitive reactance becomes suddenly very small, 1 by omega c, right? Omega is high, so this becomes very small. So whatever comes in parallel, high resistances will be shunted off, and then voltage distribution predominantly dominated by the capacitances, right, under certain conditions or under voltage breakdown. See, high voltage testing, sometimes definitely breakdown may occur. So whenever breakdown occurs, this problem will be there. The distribution of voltage will be capacitive. Now what is the problem if distribution is capacitive? If distribution is capacitive, you see the capacitances are not same. Although I have drawn parallel lines like this, but capacitances are not same because the height above the ground is not same in this case. And here also the high voltage electrode and then each of the resistors are also at different heights. Therefore, the capacitances are not same. Stray capacitances are not same. Therefore, the voltage distribution under transient conditions also, somewhere it will be high, somewhere it will be low. Therefore, some of the resistors may blow off. So, this is a problem unless we properly design. This is taken care by some adjustment. I will come back to that after some time. Let us see first stray capacitances considerations for AC and impulse. This is also problematic. For AC and impulse, stray capacitor, and in some cases, such as wire wound, this is wire wound resistors, make the resistive systems unsuitable for AC and impulse voltages because the frequency dependent characteristics will come into picture. So this is Park's resistor divider. This we will see later also. So about this stray capacitances etc. effect will be studied in detail in next presentations. But for the time being, you may note it down that it is not good for AC and impulse, because the moment frequency comes into picture, frequency dependence comes into picture, it is no more resistive, but it is reactive setup, right? So the capacitance and then inductance will dominate. Unless frequency gets cancelled out, it is not possible to get accurate results using this resistive dividers for AC and impulse. That's why for AC and impulse, resistive dividers are discouraged. Now parallel capacitors for equal stress distribution for DC. For under DC case, otherwise in normal condition it is resistive divider only, but under sudden voltage drops, just now we have seen, under sudden voltage drops, the distribution, voltage distribution follows capacitive distribution. That is why for that purpose, one way of mitigating it is to connect parallel capacitors like this between the columns. And remember, the capacitive impedance should be equal for all capacitances, so that under transient conditions equal distribution will be there. So under transient condition, equal distribution is expected between the resistors, otherwise resistors may fail. So to obtain this transient equal distribution, these parallel capacitors are connected. Now construction of resistive dividers and series resistors for high voltage measurements. What are the basic considerations? First thing is a choice of resistor. So this I will deal with in separate lecture. Complete details of all resistors and how do we choose. It is actually a very tough job to select a resistor or based on resistive material, because every type of resistor has some advantage, some disadvantage like that. Now prevention of second point is prevention of two high field gradients. One is in the construction, choice of resistance is one aspect, and then prevention of two high field gradients within the whole arrangement, that is another aspect. So now for the prevention of these high gradients etc., construction of HV electrode. So you might have normally seen why this this kind of structure, very big structures and very smooth surface, high radius of curvature is used. So the reason is actually the electric field on the surface is roughly proportional to V by voltage divided by R. R is the radius of curvature. For example, in this case, this is the radius of curvature, right? This is the radius of R. Now, if R is small, E will be high. If E is high, then corona discharges will occur like this, right? Because the air surrounding this insulation gets ionized, and then partial breakdown, but that is known as corona. Partial breakdown in air surrounding the electrodes is known as corona. It is one kind of partial discharge, it is called. So this partial breakdown will occur, and then leakage will occur into the air. So to avoid this, R is kept sufficiently high so that E will be sufficiently low. So that is, for that purpose, the high voltage electrodes are, made with high radius of curvature. This is another, when you connect a metal rod like this, here the radius of curvature of the rod will be less. So in order to prevent the corona in this region, we have to connect a sphere like this. Now increasing the effective diameter of the resistors. This is one important thing to be done. Actually, high voltage resistors are constructed using small resistors which are normally used for low voltage only, but they are connected in series and encapsulated in a cylindrical structure or shielded structure like this. You can see actually the resistors normal resistors are having this kind of structure with a small lead wire like this. So when these are used for high voltages, the diameter of this wire is very small and high corona is expected here. So to cover that, so to avoid that, this metal shields, this is a metal shield like this kind of metal shields are used in both sides, and then certain number of resistors are included inside the insulation. So like this cylindrical structure. So the resistors you were shown in the previous cases, either here, this is not a single resistor, but it is a cylindrical structure. Here also, these resistors are not a single resistor, it is a cylindrical structure inside which 4 or 5 resistors are packed and with that is shielded. So now what is happening? The effective diameter, this is the diameter, actual diameter. Now this is the effective diameter of the resistor. This is the effective diameter of the resistor. So obviously the corona will decrease from here, or surface discharges will decrease. So this is how effective diameter of the resistors will be increased. Otherwise the fields are so high that these resistors cannot tolerate them, and the surface flashover may also occur. So to avoid that, this kind of structures are needed. Now helical arrangement. Now one more aspect is to increase the diameter. So this diameter I am talking about. So if we simply keep the resistors in a vertical column like this, okay, so then this effective diameter is this much only, right? So again the field effect will be there. So to minimize that, to increase the effective diameter, this helical structure like this around the cylinder, right, like this, like as shown here. So the helix may be assumed to form a cylinder of much larger diameter across which the potential continuously decreases from the top to the bottom. So this is how it is done. So these are the Park's resistive dividers. This is built in Ohm's law, Ohm's lab. This you can see the resistors here, and this helical structure you can see here, and this is also another one. You can see the resistors here, and this is another one, and this is another company, Spellman High Voltage Electronics Corporation. They have made this kind of spheres here in order to reduce the stress. So again, this is the high voltage, this is the ground terminal, you can see. Yeah, so we will continue in our next lecture. the same topic, resistive dividers. Thank you for watching.